For this example, we want to write the quadratic function in each of a and b and c in standard form. And so recall standard form, that's what we also call the vertex form, is when we can write a quadratic function in the form y is equal to a times x minus h squared plus k. And the key to putting an expression in vertex form is recognizing a quadratic expression that is a perfect square. And that would be something that is of the form x plus p squared. And so if we were to expand a perfect square, we would get x squared plus 2px plus p squared. And so when we have an expression of this form, that means we have a perfect square. So let's start with part A, and I'll do each of these on a separate slide since they may take up a little bit of space. And so for part A, we are going to compare the expression x squared on the right side, x squared minus 8x, with a perfect square, which would be something of the form that above. And when we compare these two, we can see that for the x terms to match, we must have 2p is equal to minus 8. So that tells me p is equal to minus 4, and therefore p squared is equal to minus 4 squared is 16. So if we add p squared to both sides, then on the right side, I now have made that expression a perfect square. Namely, the right side is x minus 4 squared. Okay, so this is the perfect square on the right side. And now if we solve this for y, we've put our quadratic function into the standard or vertex form. And from this we can see that we have a vertex, for example, at the point 4 minus 16. So the real key here was figuring out how to take our original expression on the right side and to write it as a perfect square. And the key there was recognizing, well, if we add 16 to both sides, that's going to complete the square on the right side. Let's take a look at part B next. Okay, now in part B, we have the expression y is equal to x squared plus 5x minus 7. And we want to write this in the standard form, in the vertex form. And just like in part A, the key here is to say, how can I take the right side of that expression and put it into a form so that it is a perfect square on the right side. They have to look like x squared plus 2px plus p squared. And so for this to match, then what we see in this case is that we must have 2p must equal 5 in order for the x terms to match. And that means p has to be 5/2. And therefore, to complete the square, that means the constant on the right side needs to be 5/2 squared, which is 25 over 4. So what I'd like to have is, instead of the minus 7, I would like to have a 25/4. So in order to figure out how to get the 25/4 onto the right side, let's do this in 2 stages. So let's first take the 7 that we have over here and add 7 to both sides of this equation. So that would give us y plus 7 is equal to x squared plus 5x. And now we kind of have a clean slate on the right side. And what I know is I want to have the constant term to be 25 over 4. So I can add 25 over 4 to both sides. Okay, and again, we need to be careful that I have an equation, so I need to keep both sides of these equations balanced. So if I want 25 over 4 on the right side, I can't add it over here. That's going to tip the scale of the equation this way. So in order to keep this scale balanced, I will need to add the 25/4 onto both sides. And now we can solve for y. And what I can notice on the left side, since 7 is equal to 28 over 4, I could add those two constants together and write it over 4. And on the right side, we have our perfect square, x plus 5/2 squared. And this tells me in standard form, we have y is equal to x plus 5/2 squared. And now I need to subtract the constant from the left side on both sides, and that would give me minus 53 over 4. So here we've written this quadratic function in standard form, and here we can see that the vertex would be located at our value of h is minus 5/2 and k is minus 53/4. All right, and lastly, let's take a look at part C. In part C, we have a quadratic function y is equal to 4z squared minus 40z plus 16. And here's a nice little trick, and that is these can be a little bit trickier when we have a leading coefficient which is not 1. So notice we have a 4 that's in front of the z squared. And in cases like this, we can first, before we worry about completing the square, first divide both sides by the leading coefficient 4. That would give us y over 4 on the left side, and on the right side I would divide everything, each term, by 4. So that gives us z squared minus 10z plus 4. And now the right side is an expression just like we had in A and B, where we can use the same sort of form, recognition of a complete square to complete the square. So let me also bring over the constant 4 from the right side. I'm going to subtract both sides by 4, and this is going to just give me a pretty clean slate on the right side. So on the right side, I now have z squared minus 10z. And for the right side to be a perfect square, then it should have the form of z squared plus 2pz plus p squared. So now this tells me that 2p has to equal minus 10. Okay, and this is just exactly what we did in parts A and B. And then I can recognize that p is minus 5, and so p squared is minus 5 squared, which is 25. So what I need to do is take the expression I had over here, and now I figured out how to complete the square on the right side, namely by adding 25 to the right side. So I need to add 25 to the left side as well. And now on the right side, I have a perfect square. Okay, the right side is z minus 5 squared. And on the left side, I have y over 4 plus 21. Okay, I combine the minus 4 and the 25. And so what's left to do is finally solve for y. So I have equation y equals something that's written in the vertex form. So I can I can subtract 21 from both sides. and then I can multiply both sides by 4. So when I multiply the right side by 4, right, I need to multiply everything on the right side by 4. So I need to distribute this 4 both to the z minus 5 squared term, and it gets distributed to the 21 term. So now we've written the function in standard form, and we have a vertex at 5 minus 84.